This video is on molecular weights. All right, this is going to be a fairly short video. We've only got two topics to cover here. One is molecular weight. Technically, it should be molecular mass, but most people say molecular weight, including me. And this is also called formula weight. Those two terms are essentially synonymous. So we'll be looking at molecular weights and percent composition. Okay, so the molecular weight for a compound is the average weight or average mass of a single molecule of that compound, and molecular weights are expressed in atomic mass units. Remember from before, atomic mass units have the symbol AMU. So we can calculate the molecular weight of a compound just by adding up the average atomic masses of all of its constituent atoms. So, for example, an oxygen molecule has one oxygen and two hydrogens, and so the molecular weight is just the average weight of an oxygen and the average weight of two hydrogens, right? All right, now I said there were two different terms. The molecular weight, also called the formula weight. The reason for that is if you have something like water, water really does exist in discrete molecules like this. So if you call this the molecular weight, you're saying this is the average weight of one molecule that looks like this. But there are some things like like sodium chloride that really don't exist in discrete molecules. Sodium chloride exists as an array of cations and anions, right, where you've got a whole bunch of sodium cations and a whole bunch of chloride anions, right? So it's just a group of cations and anions all linked together in this sort of three-dimensional array. So the reason that people sometimes use the term formula weight is because if you have something like this that doesn't really exist in discrete molecules, you can still refer to the weight of one average unit of that, right? We call that one formula unit for sodium chloride, even though they don't exist as discrete molecules. I'm not really going to make a big deal out of that distinction. I don't think it's particularly important, but that's why this term formula weight is sometimes used in lieu of molecular weight. Like I said, generally speaking, they mean the same thing. Okay, so let's take a look at an example. One of the ones we just mentioned was water. So the first thing we need to know is the formula. And I assume you all know water is H2O. And the other thing we need is a periodic table that has the atomic masses on it. And we can calculate the molecular weight just by adding up the average atomic weights. And so for water, there are two hydrogens, and each hydrogen atom has an average mass of 1.008 atomic mass units, and there's one oxygen. When I'm writing this, I like to use OX instead of O for oxygen, because if you write O, it just looks like 0. And the average atomic mass of an oxygen is 16. Right? So the total mass of the two hydrogens will be 2.016 AMUs, and the mass of the oxygen is 16.00 AMUs, and if you add that up, 18.016, and if we apply our rules for significant figures, this number here goes out to the 100th place. This number here goes out to the 1000th place. So we should round this off after the 100th place here. So we would report this as 18.02 atomic mass units. And so again, if you had a whole bunch of water molecules, that would be the average weight of each of the molecules. All right, we'll do one that's really, really simple. The reason I'm doing this one is because I want to make a point with it. For hydrogen chloride, the formula is just HCl. That's really simple. So the molecular weight is 1 times the weight of hydrogen. My AMUs are looking horrible today. And 1 times the average atomic weight of chlorine. All right, so we get 36.458 AMUs. And again, since this only goes out to the 100th place, we'd round this to 36.46 AMU. So this is our molecular weight for hydrogen chloride. Okay, now to add another little twist on this, if we look at hydrogen chloride is composed of hydrogen atoms and chlorine atoms, right? And we can look at the isotopic abundances here, and for hydrogen, there's really only one. There are a couple of other isotopes for hydrogen, but they have very low abundances. The hydrogen 1 isotope is the most common, and this has an abundance of about 99.99%. So essentially all hydrogen atoms are hydrogen 1, and this has a mass of 1.008 atomic mass units. Now, chlorine, on the other hand, has 2 common isotopes. The more common of the two is chlorine 35, which has an abundance of a little over 75%, almost 76%. And has an atomic mass of 34.969 AMU. And the other isotope is chlorine 37. About 24% of chlorine atoms are chlorine 37. And this isotope has a mass of about 37, a little bit less, right? 36.966 AMU. Okay. And so what that means is that if you have a bunch of molecules of hydrogen chloride, right, some of them are going to be this type, about 76% of them are going to be that type, and about 24% of them are going to be that type. So this will be actually 75.78% will be that type, and they will have a mass. The mass is just going to be the sum of these two. These will have a mass of 35.977 atomic mass units, and about 24% of them are going to be of the second type with a mass of 36.966 AMU. And now if you take these two different masses and you calculate a weighted average, which is the same thing we were doing back in previous section. If you remember when we calculated average atomic masses, those were weighted averages based on these isotopic abundances here. So if we do the same thing, calculating a weighted average by assuming that 75.78% of the molecules have this mass and 24.22% of the molecules have this mass, then we get a result of 36.46 AMU for the average. All right, so my point with this, the HCl is a really simple calculation, a really simple molecule. We spent a lot of time on it. The reason I wanted to spend a lot of time on it is to make sure that you understand that the average molecular weights that we're calculating are averages for large populations of molecules. So if you have a whole bunch of hydrogen chloride molecules, this here will be the average mass of the individual molecules. But, and here's the important thing, none of the atoms themselves actually have that mass. Some of them have a mass of 35.977 AMU, and some of them have a mass of 36.966. Oops, that's not right. Let me fix that. I did my math wrong there. I'm glad I noticed that. You probably picked up on that before I did, and you were wondering what I was smoking. I just wrote that down wrong. I apologize. The second mass should have been 37.974 AMU. Sorry, I was looking in the wrong spot on my notes. Okay, so 76% of them have this mass here, and 24% of them have this mass, not this one. But none of them have this mass. Okay, this here is only the average of those other two. Okay, all right. Sorry for that. Let's go on to the next one. All right, this one's a little bit more involved. This will require us to do a little bit of careful counting of the atoms. Calcium phosphate. Calcium is a +2 ion, and phosphate is a -3 ion. So in order to make a neutral compound, we need 3 calciums and 2 phosphates. Okay. So when we calculate the average molecular weight, we're going to have to count up all of those atoms carefully. So the calcium's pretty easy. There are 3 calciums, and if you look at your periodic table, the average atomic weight for calcium is 40.08 AMU. Now we get to the phosphoruses. There's 1 phosphorus in a phosphate, but the molecule, or the formula unit in this case, has 2 phosphates in it. So that means that in total there are 2 phosphoruses here. So we need to put a 2 here. And our atomic weight for phosphorus is 30.97 AMU. And for oxygens, same thing. There are 4 oxygens in a phosphate ion, but there are 2 phosphate ions in the unit, so that means there's a total of 8 oxygens. And the atomic mass of oxygen is 16 AMU. So if we multiply these through, the total mass of our calcium is 120.24 atomic mass units. For the phosphorus, it's 61.94 AMU. And for oxygen, it's 128 atomic mass units. And if we add all of that together, we get 310.18 AMU. So there's our answer. Okay. All right. Something that comes up occasionally in these are hydrated salts. And hydrated salts happen if you have a substance, usually ionic substances. I guess this could happen with things that aren't ionic, but I can't think of any examples like that. Usually it happens with ionic things anyway. If you've got a solution of nickel sulfate and you want to get solid nickel sulfate, if you do that by taking the solution and evaporating the water off, most of the water evaporates, but some of those water molecules get sort of entrapped or connected with the nickel sulfate, so that when the water evaporates, you're left with this kind of a salt that includes some water molecules. That 2 should be a subscript here. You're left with water molecules in with the nickel sulfate, and usually there's a well-defined stoichiometric ratio. So in this case, with nickel sulfate, when this happens, each nickel sulfate has attached to it 6 water molecules, and that's called a hydrated salt. And so we write that one as it shows you there, with a little dot, 6H2O, and we would name this nickel 2 sulfate hexahydrate. Now, if you've got a compound like nickel 2 sulfate hexahydrate, if you go in the other direction and take that salt and dissolve it in water, these hydrated water molecules get dispersed out in the solution, and they're no longer associated with the nickel. So you can, when it's in solution, you consider it just to be nickel sulfate. Those waters of hydration don't matter anymore. But when you precipitate it and you're weighing it, you have to take account of the fact that there are these water molecules associated with each of the nickel sulfates. Okay, so that has to go into our molecular weight calculation. So for nickel 2 sulfate hexahydrate, if we want to calculate a molecular weight for this one, we look at the different atoms in here, and there is 1 nickel, which has a mass of 58.69 atomic mass units. There is 1 sulfur, which has a mass of 32.07. And I'm going to look at these two things separately. Right? So I'm going to say just within the nickel sulfate, there are 4 oxygens. And there are, we look at the water molecule now, there are 12 hydrogens. And 6 oxygens. Okay. You could, when you were adding them up, you could have counted these oxygens together and just said there are 10 oxygens if you want. I find it a little bit easier, it just makes more logical sense to me to look at these things in groups and not mix the groups up. All right. In fact, you could have just taken this whole group here and said that these are 6 water molecules, and if you remember from our previous calculation that water has an atomic weight of 18.02 AMU, you could have just done that for this whole bit down here. Okay. But anyway, however you want to group them, as long as you count them correctly, it really doesn't matter. It's up to you. I would just say count them in whatever way makes sense and is least likely to get you confused. All right, I'm going to go ahead and fill in the rest of the math here. Give me a minute to pop this into place. All right, so I just put in the results from multiplying all of those atomic weights by the numbers of atoms, and then when we add this whole thing up together, we get 262.856. And again, most of these numbers go out to the 100th place, so let's round our answer to the 100th place. So our molar mass then, or excuse me, our molecular mass or molecular weight would be 262.86 atomic mass units. All right. I'll mention something else. We're just talking about significant figures. When you're doing these, you're multiplying. If you look at this oxygen down here, you got the number of atoms, and you're multiplying by the average atomic weight. Okay, and when you do that, this result here has 4 significant figures. Okay, and the reason we've got that is we're multiplying two things together, and if you remember the significant figure rules, the result can have no more significant figures than the two things you're multiplying together. Okay, so this here, this atomic weight that we get off the periodic table, has 4 significant figures, and most of the weights in the periodic table have either 4 or 5. But this here, this 6, right, that's only one number. It might look like it has only one significant figure, but remember, that number is counting the number of oxygens in this molecule. So that 6 is a counting number. It doesn't have any imprecision. That number is infinitely precise, and so that 6 can be considered to have an infinite number of significant figures. Okay. That's why when we multiply the 6 by the 16, we get 96 with 4 significant figures in it. Okay. All right, here's a couple of practice problems for you. Go ahead and hit pause, and I will. I guess I'll put my math up. I'll put the math up very quickly for each one of them, and you can check your results with my results. For right now, go ahead and hit pause and work through these 3 problems, calculating the molecular weights for each. All right, so here's ammonium sulfate. We've got 2 nitrogens and 2 hydrogens, because we've got 2 of the ammonias in here. There's 1 sulfur and 4 oxygens here, and so I got a total molecular weight of 132.15 AMU. And I didn't include my units in all of these middle calculations, but I did make sure that I included my units here on the final answer. Please do that yourself also. It's very important. All right, take a look at that. I'm going to erase that and put up my results for manganese chloride, which is a hydrated salt. All right, for manganese chloride tetrahydrate, I had 1 manganese, 2 chlorines, 8 hydrogens, and 4 oxygens. And again, for this part down here, if you want to do this as 4 times H2O, if you wanted to do that, you could have. That would work out, ought to give you exactly the same result. And when I added everything up, I got 197.9 atomic mass units. So that's our molecular weight for manganese chloride tetrahydrate. All right, take a look at that. Make sure you got the same thing. And I will go ahead and put up my results for propanol. Okay, so for propanol, I had 3 carbons, 8 hydrogens, and 1 oxygen. I added all those up, and I got just a little over 60 atomic mass units. And so that is our molecular weight for propanol. All right, great. I want to take a little bit of time to go over percent composition. So let's take a look at that next. Percent composition. Percent composition basically just tells you how much of each element is in a compound. Okay, so let's look at one that we've already calculated. I assume you've got this in your notes. I'm going to go ahead and put the numbers back up for our ammonium sulfate calculation. Give me just a second to pop those up here. All right, so here's our calculation for the molecular weight of ammonium sulfate that we had on the previous page. I took out the middle part of the calculation, kind of wrote an abbreviated form here just to save a little bit of room. But our calculation shows that the average molecular weight is 132.15 atomic mass units, and of that, 28.02 AMU is nitrogen. A little over 8 atomic mass units of that is hydrogen. 30 atomic mass units of that is sulfur, and 64 atomic mass units of that is oxygen. So we want to calculate percent compositions, and percent composition always is just the part divided by the whole. When you take part divided by the whole, that's going to give you a decimal number. And so in order to convert that from a decimal number to a percent, we'll multiply that by 100%. Multiplying by 100% basically just moves the decimal over 2 spots and adds a percentage sign. Okay. So for example, for nitrogen, percent nitrogen in this compound is going to be 28.02 atomic mass units divided by the whole, which is 132.15 atomic mass units. Anytime you're calculating percentage, you've got to have the same units on the top and the bottom so that those units cancel out. Percentages are always unitless, and so you've always got to have the same units in the numerator and the denominator. All right, so we got 28.02 divided by 132.15. Like I said, if we do the math at that point, that'll give us a decimal number. So we'll take that and we'll also multiply by 100%, which moves the decimal over a couple spots. And when we do that, calculator at 21.20%. All right, I'm going to do this for hydrogen as well, and I'm going to let you do sulfur and oxygen. So for hydrogen, it's going to be 8.064 atomic mass units divided by the total molecular weight. Up to 100%. Our atomic mass units cancel out and get 6.10%. Okay. All right, take a minute and hit pause and do the same thing for the sulfur and the oxygen, and I'll put my results up here and we can compare them. All right, so when I did the calculation, I got 21.2% nitrogen, 6.1% hydrogen, 24.27% sulfur, and 48.43% oxygen. You may have gotten slightly different numbers than I did if there's a little bit of rounding error, but you should have gotten essentially the same thing. Now, when you're doing percent composition, there's an important check that you ought to do, even if the quiz or exam question doesn't specifically ask you to do this, and that is, it's always a good idea to take these numbers and add them up. And if you've done it correctly, they ought to add up to 100%, as they do in this case. Now, if there's a little bit of rounding error, you might end up with something like 100.1% or 99.8%. If that's the case, that's probably okay. But if you ever end up with 93.6% or 104.1% or God forbid 57.2%, any of those things are way the heck too far off, and without knowing anything else, you can be guaranteed that those answers are incorrect. And if it's incorrect, then go back and try to find your mistake. Do it over. Don't turn in a wrong answer. All right. So you can always check your results on calculating percent compositions to make sure you've got them right. It's possible you could have canceling errors. You could have something that's incorrect and still adds up to 100% if the errors cancel in exactly the right way. So if it adds up to 100%, that doesn't guarantee that it's wrong, that it's correct. But if it doesn't add up to 100%, that does guarantee that it's wrong. All right. So application of percent composition. Why is percent composition important? One of the ways that it's important is if you know the percent composition, you can easily calculate the amount of each element in a compound. And we can keep using this ammonium sulfate as an example. So ammonium sulfate is often used as a fertilizer because nitrogen is one of the things that plants need desperately. The three main nutrients that plants need are nitrogen, potassium, and phosphorus. So ammonium sulfate is used as a fertilizer sometimes. And let's say we wanted to know how many pounds of nitrogen are in a 35-pound bag of ammonium sulfate. Okay. So we got 35 pounds of ammonium sulfate. We want to know how many pounds of nitrogen are in there. Okay. We can use the information that we got on that last page. Okay. The last page, our calculation told us that ammonium sulfate is 21.2% nitrogen. And remember before when we talked about percentages, we said that what this means is that every 100 pounds of ammonium sulfate contains 21 7.2 pounds of nitrogen, right? Or grams or tons or whatever you want, as long as this unit and this unit are the same, then this is a valid statement. And if that's a valid statement, then you can use that to write a conversion factor, just by putting one over the other, depending on which way you want the math to work out. So we can use this as a conversion factor to go from pounds of ammonium sulfate to pounds of nitrogen if we put the nitrogen on the top and the ammonium sulfate on the bottom. Okay. So the math would look like this. Then we would set up our conversion factor like that, and our pounds of ammonium sulfate would cancel, and we would end up with .42 pounds of nitrogen. And since we've got two significant figures here, we want to write that in two significant figures. So 7.4 pounds of nitrogen. Okay. All right, so that's really it for this one. We talked about molecular weight and percent composition. There are several practice problems in the study guide, so go ahead and work through those when you've got a chance, and then we'll come back with another video.